Okay, now let's talk about discretization. We already know how to discretize the entire left-hand side, right? So we can discretize the left-hand side in the eta direction by starting from 0 to eta max. And we can have a grid point here with a spacing of delta eta. And then we defined the variables u and f and also du deta, right? We called u to be fp and du deta to be fpp, right, in our previous code. So we have these three variables all defined on the grid points. We had 3n plus 1 unknowns. We had 3n equations, and we have 3 boundary conditions. In this case, the whole left-hand side stays the same. There's no difference, right? But then we have a right-hand side. We also have another direction to be xi. And now our mesh is not just one-dimensional, but two-dimensional. So we also have a xi equal to 0, xi equal to delta xi, and 2 delta xi, etc. to xi max. In this case, our variables u and f and du deta is defined at all the grid points in eta at every xi grid point. And sometimes we have a two-dimensional solution. But the property about the thin layer Navier-Stokes allows us to not having to solve for the entire flow field at the same time. The fact that we can drop the pressure term from the Navier-Stokes removed the coupling, the global coupling, removes the influence from downstream of the boundary to upstream, right? The pressure influence is gone. And that lack of pressure influence in the thin layer Navier-Stokes is actually why, if you remember in the last lecture, you asked, can I trust the separation point if I have a large-scale separation there? And the answer was no. Is because when you have a large-scale separation, you have pressure influence from downstream to upstream. But if the boundary layer is thin, if the streamlines doesn't curve too much, the upstream influences, none, can be neglected. That allows you to precisely determine what is the solution at delta eta, just from the solution at eta equal to 0, without knowing in advance what is the solution at 2 delta eta. You only need, at every grid point in eta, you only need the previous eta solutions to know, uniquely determine the solution at a particular eta. So that allows us to advance in the eta direction instead of having to solve for the entire flow field at the same time, which is what you have to do if you do a general CFD code. All right. Okay, so this also enables us to use a small solver in the sense that every time we compute the solution at a particular eta, we don't have to remember what has happened before, what has happened in eta minus delta eta, etc. If we need anything like the skin friction coefficient, we can compute it and store that at that point, but we don't have to remember the entire flow field, remember the entire boundary layer profile at that. So that's a nice thing, right? This allows us to discretize these du deta terms in a backward difference way, in a one-sided backward difference way, okay? And you can also argue, why don't I solve this in a forward difference, forward Euler? It'll be easier. But that is only stable when you are very far downstream, in the earlier parts of the boundary layer, because of this times xi term, right? When xi is small, it is essential to solve this in an implicit way. So it is essential to discretize du deta in a backward difference way. So the discretization is going to be the discretization of this whole equation at xi equal to Ci is that partial u partial c is going to be approximated by u. So this is at eta j is going to be equal to u at ci eta j minus u at ci minus 1 and the same eta j, okay, divided by delta c. And the same thing happens for partial f partial c. I'm going to be using f at I minus f at I minus 1j. This is called a one-step backward Euler, or some people call it backward difference formula 1, like using one-step backward difference formula. A more accurate solution would be using a two-step backward difference formula, which is going to involve not only ui minus 1, but also ui minus 2. Right. How many people have studied finite difference methods before? Know those who took my class did? A little bit? Right. So, and how many people know BDF2, like backward difference formula with a two-step?
I think you can derive it, but I don't remember.
Okay, that's fine. So if you know how to derive it, that's perfectly fine with me. So I don't have to do this with you. So if you ever wanted a more accurate solution, then use the BDF2. I think the formula, I don't even remember it. I think it's like 3 over 4. I mean, maybe it's 3 over 2 and something, right?
What do you mean by two-step? Like, does it use 2 points before? Or?
2 points before, right? So you get a second-order approximation to this c derivative. This is a first-order approximation, meaning as delta c goes to 0, the error involved in this approximation, the error as a result of this approximation is order delta eta. If you use a BDF2, the error as a result of this discretization is going to be order delta eta, the delta c squared. Yes. Okay, so it'll be better as you decrease your delta c, the error decreases at a faster rate. Okay, and is that what we need? Is the partial u partial c at a particular eta grid point what we need in order to solve this equation? Not exactly, right? We need at the half grid points because all this discretization happens at the half grid points. So what do? We know how to compute the c derivative at integer grid points. How do we? Taking an average, right? Use the trapezoidal rule again. So partial u partial c at eta, let's say j plus half, then can be approximated by half of partial u partial c at eta j plus partial u partial c at eta j plus 1. So this is what we are going to use throughout our method. Any questions before we go to MATLAB and try to put this in?
Are the boundary conditions still the same as before?
Good question. Are the boundary conditions the same as before? So let's think one by one, right? The first boundary condition is f equal to 0 at eta equal to 0. Is that still the same? Yes, because this bottom is still a streamline, right? Okay, the second one is df d eta is equal to 0, which is u equal to 0 at the bottom. Is that still true? Still true, right? The third boundary condition is at eta max. The u is equal to 1. Big U is equal to 1. Is that still true? Yes, because big U is equal to small u divided by UE, so the ratio should be 1 at eta max. So all the boundary conditions remain the same. Alright, so the only difference we had is, okay, on the left hand side, we have a different coefficient up here, right, than the Faulkner-Scan equation we derived earlier. And as a matter of fact, other people derived the Faulkner-Scanner equation through what we just did. And in that case, you have to somehow argue that for Faulkner-Scanner equations, if you have similarity solutions, what we hold here are constants, right? So what we have here, xc divided by delta times d delta dxc, and also xc divided by ue times due dxc has to be constants. I think that argument is pretty complicated, so that's why we did the previous way. But if you derive it this way, you are going to derive the Faulkner-Scanner equation in such a form where our alpha prime just have a different meaning as our previous alpha.
What does the alpha prime?
The alpha prime means the alpha prime means xc over ue times due dxc, while our previous alpha is the ratio between these two terms, right? So we can actually derive the relationship between this and our previous alpha. Our previous alpha had, let me see, where do we have this? Right, our previous alpha is just this divided by this. So my previous alpha is equal to half of 1 minus, we call this alpha prime, divided by alpha prime, which is wait, is that no we previous alpha is this divided by this, so it's the other way. So it's alpha prime divided by half of 1 minus alpha prime. So this is our previous alpha, which if you simplify it is 2 alpha prime divided by 1 minus alpha prime.